Welcome to this brief tutorial over the numerical approximator, and in today's video I'm going to be giving a short introduction into the calculator portion of the project and the basic UI of the program itself. So here on the right hand side of the screen we have the numerical approximator window pulled up. On the left hand side I have RStudio, which is a very famous statistical framework. I simply have it pulled up because I want to juxtapose the functions found in RStudio with the equivalent functions found in the numerical approximator, just so we can actually see how accurate the functions found in this software is. So here at the very top, I'm going to go over the basic UI. At the very top we have the file menu. So here we can open up workspaces, save them, and export variables. On the edit side we can import variables such as data sets and matrices, while also we can clear out unnecessary variables and our workspace. Here on the analysis page, this is where you're going to perform all your multivariate statistical analyses. And unfortunately I'm not going to go over these in today's video, but I will go over them in a future video. On the last tab we have the help file, the help section, which is going to give you the basic documentation of the program, and the help file. Here we have the input. This is where you're going to input any type of constructs or computations or equations, and it's going to solve for it, and it's going to output it into the workspace. So the workspace is simply a history of all your previous inputs and their calculations. On the left hand side, if you want to store any types of variables, the variables will be stored on the left hand side in a tree order view, and it's also going to store its value, its name, and its type. So now I'm going to go over the calculator portion of the project. The calculator employs a recursive distance parser, which is an extremely robust and powerful parser that can handle almost any kind of input. So here I'm going to give some basic examples of input. It handles addition, so 34 plus 4. It also handles precedence, so if I was to say 34 plus 4 times 4, it would operate 4 times 4 before adding it to 34. As we can see here, 16 plus 34 is 50. So it can handle addition, subtraction, multiplication, division, and exponents. So we can say 2 times 2, where exponentiation is denoted by the caret symbol. And also note that exponents are right associative. So if I was to say 2 times 3 raised to the second power, it would operate 3 raised to the second power and then 2 to that power. So it would be 3 squared, which is 9, and then 3 squared, which is 9, and then 2 to the 9th power, which is 512, as we can see here. Then also we can handle parentheses as well. So we can say parentheses 34 plus 4 times 2. So this would be 38 times 2, which is 76. And it can also handle trigonometric functions such as cosine. So we can say cosine of 45. Now this is in radians. And also sine of 45. Tangent of 45. Also handles logarithms. So we can say logarithm of 45. Logarithm of, let's say, 4. It also handles natural log. So natural log of 5. Natural log of 10.5, and such. And so now what I'm going to do is I'm going to give some of the constants available in the program. So we have 2 constants right now, pi, which is 3.14, and Euler's number, which is denoted as e. So e is 2.718. So I can say e raised to the 3rd power, natural log of e, which is 1. Simply the natural log is the inverse of e. And so now we can make any types of computations. But before I do that, I'm going to give a short example of negating a number. So if I was to say -5, we would have an error in our calculator simply because negation is denoted by the tilde symbol. So if you wanted to negate something, you would say tilde that value. So this returns -5. So you can say natural log of e raised to the -5th power, which is -5. So now, since I've given a basic introduction to all the functions available and a basic calculator, I'm going to give more of the in-depth functions available. So go here to the help file. I'm going to pull this up. So here we have our basic help file. This file serves as a basic introduction to the functions available in this software. Now we have 5 value types, and before I do that, I forgot to go over the variables. So if you want to assign a variable, you simply say your variable name. So we can say this test is equal to any type of value, so 45. So here we have a variable. We can click on it, and it has its type and its value. So test is an integer, it's a value of 45. So we can now say 6 is equal to the natural log of e raised to the negative 5th power. Raise that to the 3rd power, why not? Hold on real quick, something's happening. X is equal to natural log of 34. There we go. And now we can say y is equal to 45 raised to the negative 3rd power. And so we can now say test. We can reassign variables. So now test is equal to x times y. So now test moves up to the top of the list, as has its new value and its new assigned type. And so now we can go over the value types. We have floating point values, integers, Boolean values, matrices, and functions. So now I'm going to go over the basic functions found in the software. I'm going to go over the gamma function, but before I do that, I'm going to give a basic introduction to the table itself. So the table here has the function name, the summary, the argument types, and the return value. So here, the gamma function calculates the gamma value of a given positive integer value, and assumes the integer value is positive and returns a floating point value. So gamma of 4, we can say gamma of 8, for example, or gamma of 3. Now the gamma value is simply taking the value inside, subtracting it by 1, and then taking the factorial. So we can say, so gamma of 4 would be 4 minus 1, which is 3. The factorial of that is 6. So as we see here, we can compare that with the gamma function found in R. Now also, the gamma function can take in floating point values. So we can say gamma of, let's say, 3.48, gamma of 3.48. So there we have it. Gamma of 2.34, why not? Gamma of 2.34. And so if you want to know the mathematics behind these functions, you can go here to the help file, click the documentation. This pulls up. So this gives you a brief summary of the function and simply the mathematics behind everything. So here we can go to the gamma function just real quick to show a quick example. Wherever it may be, the gamma distribution is given by the following integral. So we're simply, this gamma function is computing this following integral using the numerical methods given in the software. But that is for a later video. So now I'm going to move on to the next couple functions, which is over the ChiSquare distribution. So here we have the ChiSquare distribution, and we're going to go over the Q-chi-squared, which calculates the chi-squared quantile function for a given probability value and degrees of freedom. So we can say Q-chi-squared of, let's say, 0.95, 4 degrees of freedom. So 95% of the data in a 4 degrees of freedom chi-square distribution will fall beneath the 9.48 quantile. So we can go back here, we can compare that, 0.95 with 4 degrees of freedom, 9.48. I can say chi-squared of, let's say, 0.457 with, let's say, 5 degrees of freedom, 0.457, 5 degrees of freedom. As we can see here, 4.044, 4.044. And then now the inverse of the Q-chi-squared is the P-chi-squared. For the P-chi-squared, you give it a quantile and it calculates at what probability that occurs at. So it's a P-chi-squared of, let's say, 9.48 and 4 degrees of freedom. This should return a value very close to 95%. So we can say P-chi-squared of 9.48, 4 degrees of freedom. There we have it, almost 95%. What we can do here is our recursive descent parser is extremely powerful in that each statement in an operation can be replaced by a value or a function. So we can actually say p chi-squared of the q chi-squared of 0.95, 4 degrees of freedom, 4 degrees of freedom. So here what we do is we calculate the q chi-squared. That returns a value of 9.48, which we're going to then pass into our p chi-squared, and we can get 95%. And also we can use the arrow keys here to go through all the previous commands. You can also use the mouse wheel to go through previous commands. So now you can include this inside of some other type of calculation, times 45 for example, and it works like a basic calculator. Now I'm going to go over the normal distribution. So the normal distribution has the same functions, the q norm and the p norm. So the q norm, so before I begin, I'm going to go over exactly the differences. So the p chi-squared and the q chi-squared accepted a degrees of freedom, where in a chi-square distribution, the degrees of freedom represents the number of variables in your data set. Where the normal distribution, you don't give it a degrees of freedom, you give it simply the mean and a standard deviation. The normal distribution is for univariate variables, whereas the chi-square distribution is for multivariate normal variables. So we would say q norm, you would pass in your x value, for example, your quantile value, your probability value. So let's say 0.95, you would pass in some kind of mean, so let's say 3 and a standard deviation of 5. We'd calculate that, so now we can compare 0.95, 3 and 5, 11.22, 11.22. We could also do the inverse, which is p norm, where you feed it, so 11.22427, you feed it a quantile, a mean of 3, standard deviation of 5, and it returns exactly what probability that would occur at. So now I'm going to go over the basic root finding methods of the software, which is the bisection method and Newton's method. So the bisection method, as we can see here, performs the bisection method on a given function with starting point intervals. It assumes the function of the first floating point value times the function of the second floating point value is negative. That is to say, the given interval requires a change of signs. So because of the intermediate value theorem, if you give it our function an interval that contains the root, it will eventually converge to it. So let's say here we have a basic graph of x to the third power minus 8. We would give it an interval where you would take the function of your x, which is your a, and the function of your b interval, and that times each other needs to be negative. So if I was to feed it 2 positive x values here, our function value would be positive for greater than 2. So we need to find 2 x values where the function of your a is negative and the function of your b is positive, or the other way around. So here we have the root of the function, which is simply where this equation equals 0, and it occurs at 2. So we can choose, let's say, a value of -2 as our b, as our a, and then as our b we can probably choose 4. So we would simply say bisection of x raised to the third power minus 8, where the root is at 2, and we said -2 as the a, and then +4 as the b, and here we go. This is the approximate solution using the bisection method of 2. Now we can use the Newton's method. So Newton's method, on the other hand, if you were to go down here to the documentation, performs Newton-Raphson's method on a given function, given a function, initial value, and the derivative. So we would say x raised to the third minus 8, but let's say we don't know the derivative. It's going to use an analytical approximation, and we can give it an initial value of 1.99. So there we have it. And it is very common to actually feed the bisection method into the Newton's method. So we can actually do that right now. So we can say our initial value is the bisection method to the third minus 8, -2, -4. So there we have, we have an error here. So missing right parentheses. Unfortunately, this is all the time we have left for today, and in the next video I'm going to give a short follow-up for this on continuing our introduction.